BTEC Applied Science, we're going to have a go at a Unit 1 chemistry paper, and that's June 2017. I've done a physics one, I'll do a biology one very soon. In fact, if you're watching this, I've probably already done it. Anyway, let's go. So, write neatly in black pen. Bring a couple of black pens, bring a ruler, you might need one. Bring your own calculator. The one that you bring to every lesson, the one that you're really used to and you know where all the buttons are. Bring your own calculator. Okay, look at how many marks there are for the question. Is it just 1 mark or is it 6 marks? And that should really tell you how much you have to write. If you haven't got a clue, leave it, come back to it later, write something down. Okay, don't get bogged down. Basically, 30 minutes should be plenty of time, but you don't have time to relax. Get your skates on. If you know your stuff, you should get through it in 30 minutes, no problem. But you haven't got time to relax. If you finish early, check. And when you've checked that, check it again. This is what it says on the front of the paper. They used to do all 3 together. Now they do them separately. So 3 half-hour papers instead of 1 90-minute paper. You'll be given a periodic table. And as we'll see on this paper, that's a very, very useful thing to have. There's a lot of information on there which you will use to answer the questions, hopefully. So let's dive in. Iron is extracted from iron oxide in a blast furnace. The balance equation is blah. What substance is oxidized? Now, if we're talking kind of atoms and things, then redox, you know. But in this case, what substance is combined with oxygen? And looking at the equation, well, the iron oxide there loses oxygen. The carbon monoxide there gains oxygen to become carbon dioxide. So oxidized, it's gaining oxygen. So I reckon it's the carbon monoxide. Yeah, is oxidized. Okay. Calculate the relative formula mass of iron oxide. So iron oxide, look there, Fe2O3. So you've got 2 ions and you've got 3 oxygens, and we can look up the atomic mass in the periodic table, and pretty straightforward. 2 ions and 3 oxygens is 159.6. Okay, I always say 3 sig fig should always do, so 160 should be okay, but I've put 159.6. Why not? Give the oxidation state of iron in Fe2O3. Now, iron can have several different oxidation states, can't it? It might be +2 or it might be +3. Now, how do I know that it's +3? Well, I know that an oxide ion, O, is 2-, and I know that there are 3 of them. So we're talking 6 electrons, aren't we? Yeah, because there are 3 O2- ions. So 6 electrons there. So there's 2 ions. So the ions must be Fe3+. Okay, and then you'll have 3 positives to balance that. The answer is 3+ or +3. Yeah, 3+ or +3. That is the oxidation state of the iron. Not Fe3+. That is the ion. The oxidation state is 3+ or +3. The table shows the first ionization energy of the first 3 elements in period 2 of the periodic table, lithium, beryllium, boron. First of all, what is meant by the first ionization energy? Now, some of these answers are a bit wordy, so I've kind of done them in advance. It's the energy required to remove the first electron. Yes? Now, looking at this table, it says kilojoules per mole. So these numbers here are per mole. So the energy required to remove the first electron from a mole of neutral atoms. And that will get 2 marks. Okay. Next, explain why the first ionization energy of beryllium is higher than the first ionization energy of lithium. Well, beryllium has got more protons, okay? Lithium has got now, Harry Henry likes, so lithium has got 3 protons, beryllium has got 4, isn't it? Yeah? So beryllium has got more protons in its nucleus, so there's a bigger force of attraction between the electrons, because they're negative, and the positive nucleus. Therefore, you'll need more energy to take away that electron. Okay, because there's a bigger force of attraction between the electron and the nucleus. Explain why the first ionization energy of boron is lower than the first ionization energy of beryllium. Now, you might expect it actually to be higher because boron now has actually got, 5 protons. However, this is all about subshells. Remember SPDF, you know, there's 2 in S, and then you go on to the P shell, and the first electron in boron is in the P shell. So boron's outer electron, that should say, is in the 2p subshell, so it's further from the nucleus, and it's therefore easier to remove because it's in the P shell and not in the S shell. So it's further from the nucleus. Table salt contains sodium chloride. Sodium chloride can be prepared by reacting chlorine with sodium. A chlorine molecule contains 2 covalently bonded chlorine atoms. Draw a dot and cross diagram to show the bonding in a molecule of chlorine. So Cl2. Cl2 is 2 chlorines joined together covalently. So there's your 2 chlorines joined together. Now they both have 7 electrons, but they are sharing an electron. Now what I'll do is I'll make these ones dots. So there you go. There's 7 dots there. 1, 2, 3, 4, 5, 6, 7. And that's one of your chlorines. And I'll do the other one crosses. You could actually do all of them crosses or all of them dots. It doesn't matter. But usually it asks for a dot and cross diagram. So I'm giving it what it wants. And that is a, what is saying that? Yeah, these should be crosses, shouldn't they? Moron. There you go. Nice and neat. Beautiful. And that's my other chlorine. And that's a dot cross diagram for a chlorine molecule, Cl2. Show the outer electrons only. Yep, sorted. Describe how a chlorine atom forms a chloride ion. Well, basically, it will gain an electron. A neutral chlorine atom gains an electron to become a negative chloride ion. Oh, this is a meaty question, this one. For all you mathematicians, you're going to need your calculator. Sodium reacts with chlorine to form sodium chloride. The balanced equation for the reaction is blah. In an experiment, we used 4.6 grams of sodium reacted with chlorine. Now, the actual yield, how much we got 7.5 grams of sodium chloride. Calculate the percentage yield. So what we need to do is, if it was 100% yield, how much do we get? This is how much we actually got. So what was the percentage yield? What fraction of the calculated yield did we get? And I'll go through it. I'm not going to use the mouse. I've already done it. Here we go. So if the yield was 100%, so first of all, how many moles of sodium did we use? Well, how many moles of sodium did we use? We used 0.2. because it was 4.6 grams of sodium. A mole of sodium is 23, so 0.2 moles of sodium. That's how much sodium we used. How many moles of sodium chloride will be produced? Well, looking at the equation, we'll see that 2Na, 2NaCl, so there's a 1-to-1 ratio, isn't there? Like a 2-to-2 ratio, which is the same. So if we use 0.2 moles of sodium, we are going to get 0.2 moles of sodium chloride. So what mass of sodium chloride will be produced? Well, they've very kindly given us that a mole of sodium chloride is 58.5. We could have worked that out, but thank you very much. So 0.2 times 58.5 is 11.7 grams. So theoretically, we should get 11.7 grams of sodium chloride. What percentage was actually produced? Well, there you go. We got 7.5 out of 11.7. So that's the fraction. Times 100 is 64.1%. And that is our percentage yield. Hey, that was fun. Lots of marks. 4 marks. Aluminium is used to make drink cans. Give 2 properties of aluminium that makes it suitable for making drinking cans, Coca-Cola cans. 2 properties. I'll give you more than that. So first of all, it's resistant to corrosion. Okay. You can't say that it's resistant to rusting. There's only iron rusts, but it doesn't corrode. It would get you a mark to explain why, because it forms a protective layer of aluminium oxide. You could say that it's malleable, so you can bang it into lots of different shapes. It has a low density, so the cans don't have a lot of mass, so they're easy to transport, etc. And it's non-toxic. Okay, so it's not going to kill anybody. But 2 of them, 2 marks. Describe the structure and bonding in aluminium metal. What it wants you to do here for 4 marks is describe metallic bonding. And metallic bonding, we've learnt that. Okay, metallic bonding, I would do a labeled diagram as well. So you've got layers of atoms, a regular arrangement or lattice of aluminium atoms, or you could say ions. Yeah, a regular arrangement of aluminium atoms in a sea of free or delocalized electrons. So lots of layers of atoms with free electrons bouncing around in between, and that is metallic bonding. 4 marks. Thank you very much. If you do a diagram, don't forget to label it. Okay, now 6 marks for this one. Last question on the paper. Part of the reactivity series of metals is shown. Potassium is more reactive than sodium. Sodium is more reactive than magnesium. Explain the difference in the reactivity of these metals with reference to their position in the periodic table and their electronic configuration. So, 3 different metals. Potassium's the most reactive, magnesium's the least reactive. Let's figure out how we're going to get 6 marks. So we explain the pattern, explain why potassium is more reactive than sodium, why sodium is more reactive than magnesium. And in explaining it, we're going to talk about their position in the periodic table. So I think it would be a good idea to say what it is, as in what groups they're in, what periods they're in. And the electronic configuration, in other words, where the electrons are, because that will explain why they are more or less reactive. So I'm going to show you my answer, and my answers are there. So first of all, I've done a little sketch. You don't have to do this, but basically looking at it, sodium and potassium are in group 1, yeah, whereas sodium is in period 3, potassium is in period 4. Sodium and magnesium are in period 3. So that's their positions in the periodic table. So first of all, what I'm going to do is I'll say, why is potassium more reactive than sodium? So potassium is more reactive than sodium. They both have 1 electron in their outer shell because they're in group 1. Sodium and potassium are both in group 1. However, but the potassium has an extra shell because it's in group 4. So it's further from the nucleus. And remember that the nucleus is attracting these electrons. And also it's shielded by another shell. So the effect of the nucleus is less, it's diminished. Okay? Because of that, it's easier for that electron to escape, that outer electron to escape. Therefore, it's more reactive. Okay? I'll go through that again. They both have 1 electron in their outer shell because they're in group 1. They've got 1 electron in the outer shell. But potassium has an extra shell because it's in period 4. It's got an extra shell, so its electron is further from the nucleus, and so further from the nucleus, and it's shielded. Yes, it's shielded by that period 3 shell. Okay, so it's easier for this electron to escape, and that's why potassium is more reactive. As you go down group 1, lithium, sodium, potassium, rubidium, cesium, francium, it gets more and more reactive for the same reason. Next, magnesium is less reactive than sodium. Okay, why is it less reactive? Now, they're both, so magnesium and sodium, they're both in period 3. However, sodium is in group 1, magnesium is in group 2. And that means for your magnesium to become Mg2+, yeah, it's got to lose 2 electrons. Yeah, sodium only has to lose 1 electron, but magnesium has got to lose 2 electrons. It's got 2 electrons in its outer shell, so it has to lose 2 electrons to become a magnesium ion. So that will require more energy than it does for the sodium, and so it is less reactive. Okay, now I've written it nice and neat. I think I've explained myself nice and logically with my arguments. Okay, I reckon I've said enough for 6 marks.